Hi everyone, welcome to this new lecture in fluid mechanics. In this lecture, we'll discuss the concept of drag force on a plate due to boundary layer. So in this boundary layer theory topic, we have discussed many things regarding the boundary layer, like how the boundary layer forms and what are the different layers of boundary layer and what are the thickness of in the boundary layer created. So many things we have discussed in this topic. So in the last few lectures, we have discussed regarding the boundary layer thickness, which is denoted by delta, and then displacement thickness we have discussed, that is delta star. Then we have discussed about the momentum thickness, that is theta, and then we have discussed about the energy thickness, that is delta double star. So these are topics we have already covered in this. Now coming to this drag force on the plate due to this boundary layer. So what is the drag force in the plate will be there. So due to this boundary layer formations, let's discuss about this. So first of all, let's try to understand what is drag force. So drag force is nothing but this is the resistance of a fluid actually. This is the resistance of a fluid. So the resistance of a fluid that will be give a impact on the body, okay, or a moving object. The resistance of the fluid, we can say that exists on a moving object, and it should be always acting opposite to the direction of the motion. So that means suppose if you are dragging a object here in this directions, so the drag force will be opposite to this object, okay. So if you take an example of aeroplane, if the aeroplane is flying in the air, then the drag force will be opposite to this moving conditions, so that we can see there is a impact of drag force need to be calculated when we'll see the what is the time of flight or how it will be flies. So all these things conditions will be considered. So drag force is always keep in mind that this is the resistance of a fluid which will be acts opposite to the moving object, okay, opposite to moving. Now moving object, okay. Next, now this drag force actually depends upon the some fluid properties also, like if you see the density and viscosity of the fluid, this also plays a role in the drag force calculations. So here what we have discussed till now, I'll just give a hint. So this is the plate what we have considered here. So that plate is fixed here. So this is the, let me give the name of this plate, and the fluid is moving with an free stream velocity, that is u. So here we can write u is nothing but free stream velocity. This is free stream velocity. Now when the fluid is moving in the streamline conditions and all, this is called it free stream velocity. Now when it will be given impact on this plate, so there we have seen the boundary layer forms, okay. So though the boundary layer forms, we need to see what is the effect of drag force which is acting on this plate. So drag force will be moved in this direction because the fluid is moving in this direction, okay. And inside the boundary layer, we know that the velocity which is present, that is called local velocity, okay, that is small u, and that is called local velocity which is present inside the boundary layer. And we know that there will be a velocity profile will be created, or the velocity gradient will be formed inside the boundary layer, okay. And due to the velocity distribution or velocity changes, the boundary layer forms here. And also we know that near to the surface of this plate, the velocity will be 0, so due to the no slip condition, okay. So these are the some conditions we need to understand. And the distance from this plate to the boundary layer, that is called delta, okay. So to understand or to consider this drag force on this, we need to consider a area, small area, okay. Like drag force can be calculated, we can say that where some velocity distribution forms in better way. So here we won't consider this area in this near to this zone. Let's consider a small part or small portion which is situated. Let's suppose this is the this is not, let's give a O point, and this is the leading edge. This is the leading edge of the plate, and let it take a distance of x from this leading edge, okay. And consider this area, this small area ABCD, and which is having a length of delta x. This is the delta x length of this AB. Okay, and so this ABCD, this is actually we need to consider one more thing. We need to do these things with a control volume. We need to do the test with a control volume. So this control volume ABCD part we have taken here. The enlarged view of this ABCD we have taken here. You can see this is the delta x distance is there, and ABCD layer, which is like the volume what we have taken. So this is present, and this is the shear stress, or which is opposite in this one. Actually, this is shear stress, not this is shear force. We can consider, or even the drag force which is there, that also can be calculated from there. So the velocity profile will be like this. So in this velocity profile, we know that this is du by dy velocity gradient also. And let's consider a small elemental area in this control volume. Now let's find out the shear stress. The shear stress, that is tau naught, which is acting here, because due to this velocity gradient, we know that tau naught will be act here. In the above this, the tau naught won't work, because there will be no du by dy, because only uniform velocity is there. Okay, so du by dy is nothing but velocity gradient. It means change in velocity with respect to height. So here there will be no change of the velocity. So tau naught, the shear stress is, we know that the formula is mu into du by dy. So tau naught I have taken at this point, at the y equal to 0. So that strip what we have taken, the elemental strip what we have taken, that is the distance of y from this A point, and the thickness of this strip is dy. Okay, and the if you draw this thick strip like this plate, we can draw in this way also. Okay, now even this plate also, if you draw this plate, so when you are talking any kind of elemental strip or plate, so obviously we know that the plate will be situated like this, suppose. Okay, yeah, so this will be its length, and this will be its thickness, and this will be its width. Okay, so width can be given a v, and this is can be given a dy or delta, something will be there, and this can be given some length, delta x, or some value will be given. Anyway, so this is the tau naught what we have taken, mu into du by dy, with a height of what? At a height of y equal to 0 at this point, at the ground level. So this is the velocity distribution near to the plate y equal to 0. Now we need to find out the drag force. So drag force we can write, write down the drag force is Fd. So the drag force at this length, with this length of delta x, what is the drag force is there? Though it is a small one, so I can mention it delta Fd. So delta Fd equal to, I can write this is shear stress into area, because we know that shear stress also can be written like shear. Here this one we can write, this is shear force divided by area. So shear force equal to, or shear force, or we can say this is drag force also, both are same, shear force or drag force. Now we can write this drag force equal to shear stress into area. So shear stress what we got there, that we can write this is tau naught. Area what we will write, area we can write this is delta x is the length, and b is the width. Delta x is the length and b is the width. So this one given equation number 1. Okay, now the drag force would be most equal to the rate of change of momentum as per the rules. Momentum principle, we can say this drag force must be equal to the rate of change of momentum. Okay, now we need to go for the derivation of this momentum, and with the rate of change of momentum over, we can see only that same thing what we have taken, where that drag force was taken, the rate of change of momentum also need to be taken in the small distance, that is delta x. Now this ABCD what we have taken the control volume, let's write down the mass flow rate. The mass flow rate which is entering here, I'll show you here. See, this is the control volume is there. So what are the chances are there where the mass that fluid can be entered here? So in this way, like CD, here it is AD. These two ways are there to enter the fluid, but this side is already fixed, so there will be no entering, and this side will be leaving, existing this side. So we can write the mass rate of flow. So that one I can write mass rate of flow m dot, which is entering to the AD. So mass flow rate, we know that formula is there, that is rho AV. So we can write the integration of 0 to delta, because we see this is 0 point and this is the height is delta. So throughout this total volume, how much fluid is flowing? Only one strip is considered, means we can take only rho AV, though we are taking for whole volume. So 0 to delta integration, and rho into what is the velocity. So here velocity is u, local velocity, and what is the small strip is there. This is the small strip area is there. So that one we can write, this is B into dy, B into dy. See, I have taken only for this small strip, then I have integrated this one to consider the whole volume. Okay. Now with this one we can write, this is nothing but integration 0 to delta, and area of the strip, this is B dy, and rho into u. So we can write this is rho u B dy. This one we can give an equation number 2. Similarly, we need to find out the mass rate of flow which is entering through a CD, that we don't know. But before going to that, we can see how much is leaving through the BC. So this is BC leaving. This is entering. You can write entering, and this is leaving. Leaving is how much? Now this one is entering, and some portion will be there through this CD side, which is entering here, that we don't know, but we can assume that in this control volume, some amount of fluid which will be present through this side, through this CD, and some volume is there, that the distance is there with respect to, we can consider. So how will consider that one? How much fluid is already entered, that one with respect to some delta x length, that also will be considered. So how we can write this one, let me tell you. So this is 0 to delta, which is already entering through dot. That means the mass rate of flow which is entered through the AD. So that means rho ub dy, okay, plus the delta of that means the small area, what is that, delta by del x, with respect to what we can write, the mass rate of flow which is entered through the AD, because this one we don't know how much. So how much is entered here with respect to, if you derive this one, so we can write this is del by del x integration 0 to delta, and this is rho ub dy, bracket close, with respect to what is the distance length is there, that is delta x. Okay, so this is the mass rate of flow which is leaving the BC side. Now same thing we can find out, like what is the thing is entering to the CD side. So how to identify that one? We'll apply the continuity equation here. So we know that as per the continuity equation, we can write the mass rate of flow which is entered, that means m dot this is AD plus how much is entered through the CD. So m dot CD is equal to how much is leaving. Okay, as per this principle, what we can write here now, that much how much is entered through this CD, mass rate of flow which is entered through the CD is nothing but how much mass flow rate which is leaving this BC minus mass rate of flow which is entered through the AD. Now if I write these two equation, now see this equation minus this one. Now this equation also we have taken from that AD part only, correct? Now so if you this minus this, then this term will be cancelled. So what will get finally here? We'll get m dot CD equal to del by del x, bracket start, and here we will write integration 0 to delta, and this is rho ub dy, and this is bracket close with respect to delta x. This is mass flow rate which is entered through the CD. Because the CD part also you can see only this volume is there. This is the length of delta x, that's why we'll get this one. Now this one you can give an equation 4. Now this already we have calculated. Now but thing is, the fluid is, which is entered through this CD, that should be capital U, correct? That should be capital U. And so let's consider the momentum flux. Okay, so the momentum flux which is entered through the AD. So anyway, this what equation we have written, let's keep it. Then let calculate the momentum flux. Let calculate the momentum flux through all these sides. So momentum flux through AD. So what is the momentum flux formula? That one also we can write. Momentum flux is nothing but we can write mass into velocity. So mass already have calculated, correct? Into this velocity will be and will multiply that one. So that one will write 0 to delta. Okay. What is the momentum flux through the strip with the thickness of this one? Okay. If this first we need to consider for the small strip. The small strip also same thing. Here it is like how we have drawn this one. Similar way I need to consider this one also. This is dy and this is the width is there. This is b. This one b. Okay. Now then we can consider the total control volume. The total whole volume is there. That's why I am writing 0 to delta integration because we am considering for all. But what about this mass of the through the strip will be there? So that one we have calculated. That is nothing but rho u b dy into the velocity. So local velocity, that is u. So this is mass and this is velocity. So mass through the strip into velocity. So this one we can write integration of 0 to delta and rho u square b dy. This is momentum flux entered through the AD part. Now this one again we can give an equation number 5. Okay. Now similarly we need to find out the remaining two also. Here we can calculate what the momentum flux again, which is entering through the BC or leaving through the BC. So I'll write shortly momentum flux which is leaving BC. So this also we can write the same formula like mass of momentum, what is the mass is there into that velocity. So 0 to delta, and here we got what rho u square b dy plus we got the same thing. I hope let's check it once. Yeah, this is u is there. Now if you just multiply the velocity with that, then we'll get the u square in that actually. That's why directly I've written here, because see here u square we have written that the momentum flux to the AD, again similar thing, momentum flux for the BC which is leaving, then this one along with that the delta part of this control volume. So that's why I'm writing this 0 to delta rho u square b dy. Again same thing I need to write here. This is del by del x bracket start, and this is 0 to delta into rho u square b dy into delta x. This is the momentum flux which is leaving the BC. But here also we can calculate now this one equation, we can give equation 6. All the equation we can give some numbers. Now again we can write this is momentum flux which is entered through CD. Now we can calculate because we know the mass flow rate. Okay, so mass flow rate we can write this is del by del x, again square bracket start, and this is 0 to delta and rho u b dy, and this is delta x into the velocity. So velocity now we need to consider here capital U. What I told you previously in the, if you see here, I told you that the velocity which is coming through this side is that is CD, that is capital U. So that capital U, the velocity we need to write here. Okay. Now this one we can give. We can equation number 7. Now here the velocity is constant, so that we can take this is differential and integral equations. Now we know that the rate of change of momentum need to be calculated. So let's calculate the rate of change of momentum through the control volume. The rate of change of momentum through the control volume. So obviously what is the momentum entered, or what is the momentum of the fluid through this AD, that all the things we need to check it. So how much is left? Momentum flux which left through BC minus how much entered. So momentum flux through AD minus, you can write this is momentum flux which is, this is entered, and this is entered through CD. So this is the formula for this, like you can calculate from here. Now all these equations are now we need to kept in this concept of rate of change of momentum through the control volume. So what are the equations we got? Just we need to write all these equations and we can solve it this one. So what is the first BC contents of two terms are there. So I'll write from here starting. So this is integration 0 to delta, and this is rho u square b dy plus del by del x bracket start 0 to delta, and this is rho u square b dy bracket close delta x. This is the momentum flows which is left, this one, equation 6, minus AD part is very simple. You can write only small equation is there, rho to 0 to delta rho u square b dy, and minus CD part is this one, del by del x bracket start 0 to delta rho u b dy, and this is whole multiplied to del x into capital U. So capital U can be taken inside also, no issue. Now if you solve this one, obviously this part will be cancelled, so remaining two part will be there, that is nothing but we can write this is del by del x bracket start, and this one we can write 0 to delta rho u square b dy minus, just have taken the del by del x common, this one and this one let's take common, so rho u b square by dy minus, we'll get equation again this one 0 to delta 0 to delta, again this one we can write rho small u capital U b dy bracket close delta x, because delta x here also delta x is there. Now again we can solve this one, we can write in this way, like del by delta x bracket start 0 to delta, and here what I'll do, delta x already the outside is there, dy take common. Okay, one more thing I'll do here, so I'll take the rho b outside, rho and b, this rho and b outside, and then we can write this is 0 to delta bracket close u square minus small u capital U bracket close, then we can write this is dy also take common outside, integral part, and this is delta x. So this is nothing but the rate of change of momentum, okay, through the control volume. So this one we can give equation 8. Okay, now as I told you that both the equation need to be equalized, so we have seen that the delta FD what we got that previously, that is tau naught into b into delta x. So we know that drag force which will be acting on the plate, that will be opposite to the fluid motion. So this one we can write this is minus, though it is moving in the reverse direction. So some reference we have taken, so that one need to be considered, minus of tau naught b dx. Okay, so this one we give equation 9. So now we need to, according to the momentum principle, what we need to do, these two values should be equalized, these two values should be same. So as per the momentum principle, we can write equalize these two equation, that is minus tau naught b delta x, and this equal to what we got, delta x rho b. Okay, rho b take it total outside also you can take it, so rho b and del by del x bracket start integration 0 to delta, and this is small u square minus small u capital U bracket close into dy bracket close into delta x. Now this is the term is there. Now just we need to solve it, we'll get the final equation, that's it. So what I'll do here, just cancel the b into delta x part in the both side, b into delta x, so b into delta x in the both side, and then what is the next term will be there, so I can write this is minus tau naught, that one I can write this is yeah, rho del by del x bracket start 0 to delta bracket again start u square minus small u by small u capital U, and this is dy bracket close. Okay, now what I'll do, I'll just take this minus term this from this side to this side. I'll insert in that directly bracket inside the bracket. So again, one more step I'll also do it here, like tau naught equal to I'll write this is okay. One more thing. So let first make it inside to this. So rho into del u by del x bracket start, and this is 0 to delta minus. I told you to I'll take it inside. So if I take it inside, then what will be there? Bracket start, then that will be small u capital U minus u square bracket close, and this is dy. This is the term will be there. Again, what we'll do? This rho delta by del x. Okay, now we'll do one thing. Let multiply a capital U square here and divide here. That means I'll do it here. Let's see. Rho del u by del x bracket start. This is integration 0 to delta u square, multiply here and divide here also. Now by dividing, what we'll get? Or you take a common from the u square. U square is not there. So what we'll get actually? We'll get u by capital U. U by capital U minus small u square by capital U square. I multiplied here, divided here. So multiplied u square and divided u square means u will be cancelled, only capital U will be there, and this is dy bracket close. Now the next half I'll write here, so it will be completed here. Now the next thing what I can write here, tau naught. This is tau naught. Now this u square will take it to outside. So see this rho and this u square I'll take it to outside. So after taking this outside, then rho u square take it to the left hand side. So it will go tau naught by rho u square. Tau naught by rho u square, that is equal to del by del x. This is bracket start, integration 0 to delta small u by capital U. Here now see in this part, take common of small u by capital U outside. Then after taking common, what will get? 1 minus small u by capital U, and this is here will get, this one will get, okay, this one will get actually dy will be out here, it's hanging, bracket close. Now if you see this equation, actually this equation is nothing but momentum thickness. We have studied the momentum thickness theta. So just put the value of that, what will get? Tau naught by rho u square, this equal to del by del x into theta. So theta is the nothing but this one. This is momentum thickness, what we got previously. So this is our final equation of this, and this one you can give an equation number 10. And this equation also called as von Korman momentum integral equation. Von Korman momentum integral equation. Okay, and this equation can be applied for the boundary layer concept or boundary layer flows, where we can get we know that we have the laminar boundary layer, correct? So it can be applied for this laminar boundary layer. Along with that also we have seen the transition boundary layer, okay, and also we have seen that turbulent boundary layer is there. So these are the boundary layers where we can implement this equation. So this is the total equation what we got. This is the final one. You can see this, and I hope you understand this concept of drag force on a plate due to the boundary layer. So though this boundary layer is there, that's why what is the impact of drag force on this plate, that need to be calculated. So that's why we have calculated here. I hope you understand this concept. Still, if you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you.